Welcome to Spring LIB.
Alrighty, so we're going to start out with using this relation to find the velocity here. So d divided by delta t, and of course the d then being replaced with 2 pi r to account for the circumference, the motion of the swinging, and we divide this then by the period t. And now we can go ahead and do this for the 2 different motions that we're getting out of this. We have the v1, and this is going to be equal to the 2 pi times the radius 1 divided by 1 over the frequency 1, which is given to us. Then we go ahead and we clean this up a little bit. We have our 2 pi times 0.6, and then this is divided by 1 over 8. And when you go ahead and compute that, you get 30.2 meters per second. We'll do the same with V2. For the second bit of data, 2 pi R2 by 1 over frequency 2. And this is equal to 2 pi multiplied by 0.9 and divided by 1 over 6. And when you go through this, you get 33.9 meters per second. Okay? And from this, you can see that frequency 2 gives 6 revolutions per second greater speed per ball. 6 rev per second, greater speed for the ball. 6 per second greater speed for ball. Speed for ball. Excellent. Okay, so we'll leave that box. That's our first answer. All right. And we want to find out the centripetal acceleration, which I'm going to do right over here. So the centripetal acceleration is going to be equal to this v1 squared divided by the radius 1. And from this, we can go ahead and plug in 30.2 squared divided by the radius 1 being 0.6. And when you go through the math here, your centripetal acceleration is 1,520 meters per second squared. And last but not least, we want to go ahead and find the centripetal acceleration for the other situation. So we just did it for the frequency being 8. Now we're going to do it for the frequency being 6. So same situation again. And this is going to be now the v1 squared, which is 33.9 squared. And go ahead and divide this by 0.9 squared. And that's equal to 1,277 meters per second squared.